This lesson deals with supplemental problem 10.5. You can find this problem in the ECE202 ebook in the Chapter 10 supplemental problem starting on page 9. This time domain circuit is a model for a spark gap. The way this works is when the switch is closed, I've got current flowing in this path because the inductor looks like a short circuit in steady state. When you open this switch, the current in the inductor cannot change instantaneously, and so the same value of current will now flow through a very large resistance, creating a very large voltage. And this is how a spark plug works in a car. We have current flowing through an ignition coil. We break the contact and we force the current to go through a very high resistance, which is really the mixture. I'm modeling this as a 100K resistance, but you'd have to know more about what the mixture is. Let's transform this into the S domain. So we have a step function of 12 volts. We have an initial condition on the inductor model as a step current source in the same direction as the initial condition. And then, of course, this switch is going to open at t equals 0, and we've got a voltage across the 100K resistance, which we'll call V out. I'd like to do the following three tasks. First, use the Laplace transforms to solve for V out of t. Second, use PSpice to simulate your circuit and plot V out of t for 5 time constants. And then lastly, give MATLAB V out of S prior to doing a partial fraction expansion and have it find V out of t. And then also have MATLAB plot V out of t for 5 time constants. So our first task is to use a Laplace transform, so let's use our 5-step algorithm. First one is to find the initial conditions of our reactive component, which is our inductor, which looks like a short circuit in steady state if in a DC circuit for a long time. Our switch is still closed, so we have 12 volts and just 100 ohms. So the current that's flowing in this circuit prior to the switch opening is going to be 12 volts divided by 100 ohms or 120 milliamps. Step 2, transform our circuit into the S domain, which is already done for us. And now we can put in that initial condition of 120 milliamps as a current source in parallel with our inductance, which has an impedance of S times L, and it was 1 millihenry times S. Step 3 is to analyze the circuit. Got two sources here, so we could use superposition. If I set this equal to 0, then I could solve for this voltage as a voltage divider. So it'd be 100K over the sum of these impedances of 100K, 100 ohms, and 1 milli times S. And that's right over here. And then we're going to multiply that by our voltage, which is 12 over S. Set this source equal to 0. It's a short. That's going to put this in parallel with this. So I could use a current divider. And I want the current in this element and multiply that by 100K. But if we use the impedance current divider, it's going to be the other impedance, which was S times L, over the sum of SL plus 100 plus 100K, and then times our current, which is 120 milli over S. All right, I can clean all this up. So I have an S. In my denominator, I'll pull out a 10 to the minus 3, so I get an S there. And then I have 100.1K here, and then dividing that by 1,000, I get 100.1 times 10 to the 6th. And then in the numerator, I've got 12 times 1,000 times 100K. So I've got the 2Ks giving me 10 to the 6th. And then 100 times 12 is 1,200. So that'd be 1.2 times 10 to the 9th, or 1.2 giga. Likewise here, I'll pull out a 10 to the minus 3. So I've got an S, and then I've got 100.1K divided by 1,000. The S's cancel. The 10 to the minus 3 and the 10 to the minus 3 here will cancel also. And then I've got 120 milli times 100K. The K and the milli cancel. And so I have 100 times 120, and that's 12,000. Let's find a common denominator. It should be this term S plus 100.1 times 10 to the 6th times S. Just bring this term over here, and then this term I have to multiply by S to get the same denominator, so 12K times S. Highest power of S in the numerator is 1, and the denominator is 2, so we have a proper rational function. So we can do our partial fraction expansion as sum K1 over S plus K2 over S plus 100.1 meg, or times 10 to the 6th. Solving for K1, we'll take our expression, multiply it by S, and let S equal 0. So we have 1.2 gig divided by 100.1 meg, and that's equal to 11.988. Likewise for K2, we'll multiply by S plus 100.1 meg, and let S equal minus 100.1 meg. Terms cancel, so you have 12K times a minus 100.1 meg plus 1.2 gig divided by a minus 100.1 meg. This turned out to be 11.988K. So we can express V out of S as K1 over S plus K2 over S plus 100.1 meg. Take the inverse Laplace transform. This is our step function of 11.988, a scalar here of 11.988K, and then 1 over S plus alpha is e to the minus alpha t. Again, let's write this as a time constant, so the reciprocal is 9.99 nanoseconds. Our function then is 11.988 plus 11.988K times e to the minus t over tau, where tau is about 10 nanoseconds. Units are volts, and this is true for t greater than 0, or you could use the u of t function. What's interesting here, if you let t equal 0, you get the summation of this term and this term, which is 12,000 volts. So So we're going to spike a voltage across that switch, going from 0 volts to 12,000 volts as we open the switch. I'll see if we can verify this in PSpice. Our time constant was 9.99 nanoseconds. That's equal to L over R Thevenin, which was 1 milli over 100.1 K. I'm going to plot 5 time constants, which is 5 times this, which is 49.95 nanoseconds, so we can watch the thing decay to 0. All right, so number our nodes, I'll call this 1, 2, and 3. Title, call it the spark gap. Dot end. Dot probe, which will plot all of our variables. So for our transient analysis, we'll stop our graph at 5 time constants, which is 49.95 nanoseconds. Divide that by 200, that would be my print step. So I get a minimum of 200 points on the screen. Start plotting at t equals 0, and then let's pick the ceiling step the same as the print step to get a nice smooth curve. Now we do have an initial condition at t equals 0 plus, and that was 120 milliamps. So we're going to add that term into our description of the inductor. So I got a battery between 1 and 0, 12 volts, an inductor between nodes 1 and 2 of 1 millihenry with an initial condition, R1 between 2 and 3 of 100 ohms, and an R2 between 3 and 0 is 100K. So running the file, I plotted node voltage 3, and you can see here I've got a voltage that jumps up to 12,000 volts and then starts to decay down to 0. And here's our 49.95 nanoseconds, and it's dropped to 92.734 volts. That's actually a 99.2% drop from the initial value. Again, almost 0, but we really have to go out to infinity for this to actually be equal to 0. Let's just check this one point in our equation just to see if that is exactly what's happened. Let's take our equation for V out of t, which is 11.988 plus 11.988k times e to the minus t over tau. Now we're going to pick 5 as the ratio. In other words, plugging in t equal to 49.95 nano divided by the time constant, which was 9.99 nanoseconds, you get minus 5. That turns out to be 80.7745. You would predict 92.763 volts at that instant in time, and we measured in SPICE at 92.734. So again, pretty close. The default accuracy of SPICE is 0.1%, and we can make that tighter, but that's pretty much the same result. Our final task is to use MATLAB to verify our results. Let me make this a little bit larger so we can see it. Using the student version of MATLAB, so I get the edu prompt. First declare my variables, which are S and T, so SYMS and then ST. Let's give MATLAB the value for V out. I'll call it V. But let's do that before we did a lot of the algebra on the expression. So back on page 10, we had that V out was equal to 12 divided by S times 100K divided by 1 milli times S plus 100.1 K. And then we had a second term, which is 120 divided by S, but it was also an S in the numerator, so let's cancel. Then we had 10 to the minus 3 times 100K, so that's just be equal to 100. And then divided by the same denominator, which is S times 1 milli plus 101.1K. Hit enter and you get the expression back. Then we'll take the inverse Laplace transform of our variable v, which is a function of s, and then our results will be as a function of t, and I'll call that little v. And this is the resulting expression. It's a little hard to read, so let's hit the pretty command, and we get the ratio of these two numbers, which turns out to be equal to 11.988, and the ratio of these two, which is 11.988k, and this is e to the minus 100.1 times 10 to the 6th. Let's use the EasyPlot command to sketch our results. We'll plot V from 0 to 50 nanoseconds. And here's the resulting graph. And you can see, just like our PSpice simulation, we go from 0 volts to 12,000 volts as we cross 0. And eventually, at about 5 time constants, which would be about 50 nanoseconds, we've decayed to almost 0. In reality, this is about 93 volts. One last comment about the spark gap. This is a very, very short time scale. In other words, this is 50 times 10 to the minus 9 seconds. If we were to plot this on a millisecond scale, this pulse would look something like this. We're going from 0 to 12,000 volts and basically back to 0, it almost would appear to be instantaneously. Now, if the gap is just air will break down at several thousand volts, so you get a spark or an arc. And that would cause the resistance to go from a high value to a low value. If it's gasoline, it'll break down again at some particular voltage, and that'll trigger an explosion. And that'll drive the pistons, basically transfer the energy of the gas to the wheels of the car. And this is supplemental problem 10.5.